In organic chemistry, sometimes we need to determine the molecular structure of a compound. However, this structure sometimes cannot be analyzed by analyzing a chemical reaction with other compound. So we need other tools. In this episode of video, we will introduce you with a method that can determine the functional group in a molecule. It is called infrared spectroscopy. Infrared spectroscopy utilizes IR radiation to determine the type of bond in a molecule, as bond would usually interact with only one specific wave number of IR radiation. Therefore, by determining the transmittance of IR radiation after passing through the molecule, we can determine the type of bond in the molecule, and therefore we can get the functional group in this molecule. So now we will start with the general introduction of IR radiation. Infrared radiation is a specific type of electromagnetic wave. It has the wavelength between 700 nanometer and 1000 nanometer, which is within the range of frequency of 300 gigahertz and 430 terahertz. It is generally not perceivable to human beings. IR radiation, just like all other EM waves, interact with most of the matter around us. When IR radiation incident on, for example, a molecule, this could be water or carbon dioxide or any kind, IR radiation would transfer infrared energy to the molecule and cause it to vibrate. Vibration here generally means the bond are bending and stretching. Stretching generally means that the bond are changing their bond length, and bending generally means that they're changing their bond angle. So for the cases that I mentioned earlier, when an IR radiation incident on CO2, you may suggest that their OCO bond angle are changing and the CO bond length are changing also. You may assume that it is in spring, that two atoms are on each side of the spring and the spring are alternating between contraction and extension. So as IR radiation passes through the bonds, some of the energy is absorbed. The energy is transferred to molecule as vibrational energy. Since different type of bond would absorb energy of IR radiation of different wave number, we will try to determine the bond in the molecule by measuring the transmittance of every wave number in the IR region, so that we can see that the type of bond that are absorbing the IR radiation, in other words, that the bond are present in the molecule. So here is a diagram of an IR spectroscopy you would see in lab.
Y-axis is transmittance in percentage. It shows the percentage of IR radiation that managed to come through the molecule unabsorbed. And 100% transmittance stands for no absorption, and 0% means absolute blockade. X-axis is wave number, a term you might not have heard before. It is the reciprocal of wavelength. So this graph shows the relationship between IR transmittance on the corresponding wave number. As we know, different types of bond would absorb IR of different wave number. Now that from the graph, the low transmittance, which means high absorption, at a certain wave number indicate the presence of a certain type of bond. The absorption on a specific wave number range for each type of bond are shown on the data booklet. But not every 12 on the graph indicates a bond, though it is true for most of the times. IR spectroscopy is divided into two parts, diagnostic region and fingerprint region. Diagnostic region is the part that wave number is larger than 1500. We call it diagnostic region because we can use the shape of the graph to deduce the types of bond present in the molecule, while the fingerprint region can directly point to a specific type of compound. For example, we have propan 1 node and propan 2 node. They have the same type of bond, therefore their diagnostic region's graph have almost identical shape. So it is impossible to deduce the structure of this compound solely from the diagnostic region. When this happens, we use fingerprint region to analyze the type of compound. However, without the database of fingerprint region, it is impossible to determine the type of compound. Thus, for compound with the same functional group, it will be very hard to determine the structure solely by IR radiation, whereas we might need other analytical method to determine the exact structure.
Hello everyone. This part of the episode will show you how does IR spectroscopy works in real labs. And now you are seeing the actual IR spectrometer device. The organic compound we are going to test are all liquid under room temperature. However, we cannot directly put our liquid sample into the device because the device is not designed to do so. It is designed to test for solid objects. Therefore, to be able to test our sample in this device, we must process our sample first. We will drop the chemicals, for example ethanol, onto ionic compound, which in this case is potassium bromide crystal, and then put the crystal into the device to carry out the experiment. You might wonder that KBr would interfere with the experiment result as it might interact with IR. The truth is, ionic compounds have very strong lattice structure, which fix the position of atoms and generally prevent it from interacting with IR radiation, thus minimizing the interference with IR spectroscopy. For this device, we need to make our potassium bromide plate into a very thin, circular, and almost transparent plate so that it can act as a carrier for ethanol. There are several steps in preparing it. First, large KBr lumps are needed to be ground into KBr powders. We then put the powders into this pack of metal molds, which would then be placed into this tabulating machine. The mold would be pressurized to at least 20 million Pascal to turn the KBr powder into a tablet. We then remove the mold and put the plate into this frame of the device. As now the carrier for liquid sample is prepared, to start the experiment, we can just drop the samples onto the KBr plates. Now we have everything prepared for the experiment, and now we shall start it. As we are unable to create a vacuum environment, the air inside the device would cause background interference. So we would carry out the experiment without the sample to zero the device so that to eliminate the interference. All actions are done from computer, and you can see it. After this zeroing experiment, we put in our sample and carry out the experiment. Now we have obtained a graph of IR spectroscopy in transmittance. The one last thing we need to do before analyzing it is to zero the interference of air. First, the graph needs to be changed into an absorption graph. Then we click Automatic Baseline Correction, which yields a second curve that is without interference. The original curve is then deleted. We then change the graph back into transmittance and may start analyzing the graph. Now we shall start to interpret the experiment result. There are two apparent trough in the diagnostic region. The first one we're seeing is here, around 3500, and the second one is here, around 3000. With reference to data booklet, we may know that it is OH bond in alcohol and CH bond. And the part you are seeing here is fingerprint region, the part that you don't really need to know about.
As you have learned what IR spectroscopy is, the following video will show you how to analyze an IR spectroscopy diagram. First, we will start with ethanol, with the molecular formula of CH3CH2OH. There are only 4 types of bond within this molecule: carbon-hydrogen single bond, carbon-carbon single bond, carbon-oxygen single bond, and oxygen-hydrogen single bond. Carbon-hydrogen and carbon-carbon single bonds are present in most organic molecules. So when trying to identify an organic compound, we usually would ignore those 2 types of bond. With reference to data booklet, carbon-oxygen bond would have a strong trough on wave number from 1050 to 1410. And oxygen-hydrogen bond in alcohol would have strong and broad trough on wave number from 3200 to 3600. These 2 troughs are quite observable on the diagram. Then we proceed to ethanol with molecular formula of CH3CHO. The only type of bond that requires attention is carbon-oxygen double bond. Data booklet suggests that carbon-oxygen double bond in aldehyde, ketone, carboxylic acid, and esters would have a strong absorption at 1700 to 1750, just as you are watching here. The final demonstration is ethanoic acid. It has a molecular formula of CH3COOH. Carbon-oxygen double bond and carbon-oxygen single bond and oxygen-hydrogen single bond are the bonds that worth attention in this case. They have absorption on 1700 to 1750, 1050 to 1410,
and 2500 to 3000 respectively, which are shown here on the IR spectrum. Now we will start to analyze the unknown compound. This is the compound that you need to utilize 3 analytical tools to deduce its molecular structure. Its IR spectroscopy lies here. It has observable absorption on wave number from about 3200 to 3700, 2800 to 3000, and 14 to 1500. These 3 absorption correspond to, with reference to data booklet, is oxygen-hydrogen single bond in alcohol or phenols, carbon-hydrogen bond, and carbon-oxygen single bond in alcohol, ester, or ethers. This result gives the possibility of alcohol, phenols, esters, and ether. However, it cannot be phenol, as the IR spectrum shows no carbon-carbon double bond. It can't be ester, as it doesn't have carbon-oxygen double bond. The fact that it has an oxygen-hydrogen bond eliminates the option of ether. Therefore, it can only be alcohol. But for how long its main chain is, and what exact shape is its structure, we need assist of other tools.